All right, so I think I'm mostly not going to be watching questions or anything as I talk, but I'll posit a few points to check in on what might be happening on the question front. And I'm expecting that the kind of unidirectional part of this, that's not the question, should take a little under an hour. And that should leave plenty of time for questions. I guess discussion's a little hard by this medium, but we might approximate it. So I'm going to be telling you about some work in applied cryptography and formal methods, which is joint with a number of students I've listed at the bottom of this slide. Let me set the stage first by telling you about the kind of cryptographic process that we wanted to make better in some way. So many of you probably know that when you want to visit a website, there's quite a lot going on behind the scenes. Your browser wants to talk to some web server, and the web server has a public and private key pair and a certificate that some authority generated, basically saying whoever knows this private key corresponding to this public key is the following company. So when your browser wants to talk to the web server, the first thing it does is it goes through what's called a key exchange protocol to establish a shared secret that, in theory, only these two parties know, which can then be used as a symmetric key to drive the rest of the interaction. But before we're ready to believe that we've established the secret with the right party, we get a hold, as the browser, get a hold of the public key and the certificate and ask the server to prove it is who it says it is by generating a digital signature using its private key, which can be checked on the browser. And after the browser is satisfied by this process, then we can go into using symmetric key cryptography for the main part of the interaction, where you say download the contents of a page. So that cartoon, I hope, got across the idea that we have public key and private key parts of this process. The public key part only runs once per session. This is still often enough to matter if we think about the performance of this code, because when you visit a single web page, you might actually be making many requests, starting many HTTP sessions to, say, grab a whole bunch of images that appear on that page. So the people behind the major browsers care about the performance of this code. And it's actually pretty tricky to get this code to be simultaneously correct and fast, as well as secure. And what I was really surprised to learn is that the biggest challenge in that domain is arithmetic. We want to get modular arithmetic with big integers to be sufficiently fast. How hard could that be, right? There must be people who specialize in this, and indeed there are. Basically, in this world, there's a moderately large space of different algorithms that matter for different cryptographic standards. And there's a smaller but still non-trivial set of different prime numbers, large prime numbers, that are used as moduli of arithmetic in different standards. And then there's a smaller still, but still non-trivial set of different categories of hardware architectures that really deserve different implementation strategies to get good performance. And what I was shocked to learn when I first dipped my toes in this area is that state of practice was, whenever someone picked a new element of this three-way cross product, one of the experts would spend significant effort rewriting all the arithmetic code from scratch in C or assembly, because that was viewed as necessary to get good enough performance. So it seemed like a big opportunity to do things better. And therefore, we introduced a project called Fiat Cryptography, which you can think of as a kind of compiler that knows how to build code for these different variations on cryptographic algorithms. And as a bonus, it has a machine check correctness proof, which is built using a theorem-proving software package called Calc. And our tooling has now been adopted by a number of high-profile open source projects, like the cryptographic code behind both Chrome and Firefox. And so now a majority of secure web browsing connections by browsers are initiated using code that was generated with the theorem prover in our project. So basically, this was a case of trying to bridge the gap. Visualized here, we have the real world represented by the folks maintaining popular software packages like OpenSSL, Unfortunately, our code is not quite an OpenSSL due to licensing issues, but that's a whole other story. We'd like to get there soon. And on the other side, the ivory tower, where people like me and my students live, knowing about formal verification and compilers, and figuring out a way to bridge this gap where there's a compelling enough sales pitch for why the people in the real world would like to replace their manual effort with our kind of fancy seeming formally verified compiler. So to set the stage for the rest of that story, I'm first going to try to, since I know this is a broad CS audience, catch people up on where the kind of verification technology that we're using stands today and what it's all about, why we should trust it. Then I'll give a little more of the motivation on the kind of code that we're concerned with here within the broader domain of cryptographic software. Then I'll spill the beans about how our tool works in particular, and then tell you a bit about some further directions we're exploring to get our formal guarantees to apply to even more of a complete cryptographic system. All right, so I'm going to start with some kind of cheerleading for formal verification. Here's a fun quote from the memoirs of Maurice Wilkes, who was an early developer of computer systems, basically stating a realization that we take for granted today, but which must have been quite a shock back when he had it, which is that with computers, we don't actually spend most of our time programming them, even if that's the way we describe an activity. In practice, we spend even more of our time debugging, catching the mistakes in our code. And we're all used to this. We get a kick out of watching the students in our introductory programming classes come to terms with this realization. But every so often, it is a good idea to question your assumptions, make sure you still believe them. And I think it's natural to wonder if there are better ways of going about programming, so we don't spend quite so much time dealing with mistakes. So that's what formal methods is all about. Probably everyone's heard about it, if not engaged in it themselves. Basically, what we're trying to do is take effort that conventionally goes into debugging and move it into formal proof of the correctness of systems. Take effort that traditionally goes into testing, where we have to make careful lists of different scenarios to exercise a system with, and move some of that effort to specifying, where we give completely general mathematical characterizations of which behaviors are correct. And take some of the effort that we put into auditing code for implementations and move it into auditing those specifications, which we hope are significantly more tractable to read. Because, for instance, the specification doesn't need to include optimizations. It's math. It doesn't itself run. It just describes a system that runs. So this is the game that's been recognized since at least the 1960s, probably earlier. And there have been some famous skeptics out there about the prospects of formal verification. Here's a quote from a paper that's widely referenced among skeptics, which basically says, yeah, sure, in theory, someone could write a mathematical proof that a realistic software system is correct. But there's so much complexity and even boring detail behind a realistic system that we doubt humans will have the patience to build these complete proofs with full rigor, let alone check someone else's proof. And I would say from today's perspective, these authors were both right and wrong. I think they were right that it's asking for way too much for humans to be reliable evaluators of completely rigorous proofs about large software systems. But the twist is, we don't need to ask humans to do that evaluation. So let me tell you about the proof workflow of the future for mathematically assured software systems. There's a future guy at the top right standing on a rocket ship. So we want proof engineers to write down the statements of theorems in their favorite IDEs and also write out proofs in the same IDEs. They're not working alone. They're drawing on ecosystems of libraries for different mathematical theories, different styles of reasoning about program correctness. And of course, they check their code into version control. which helps them work with collaborators who are proving other theorems that can be linked with the first guy's theorems to prove something even bigger. We connect all this to continuous integration, which is constantly checking that we haven't introduced unconvincing proofs into the system. And we can do that automatically because we have a proof checking algorithm that's able to look at logical arguments in our standardized format and confirm that they're convincing. And the proof engineers are no longer needing to review each other's system implementations or even each other's proofs. They only have to review each other's theorem statements to make sure everyone's proving what we wanted them to prove, so we don't accidentally decide I've verified my software when I proved some degenerate property about it, like I don't know, it always returns a number when we actually cared what number it was. So the twist is, this is actually how people in my research area are going about their lives every day. All these tools exist. This stuff is standard. And most of this was a lot less standard 20 years ago. So folks who have ideas about formal methods based on earlier waves of skepticism might appreciate seeing that we've progressed to this point with the tooling. Most important element here, we don't have to make people read proofs and decide if they're convincing. We do this using software packages called proof assistants, which are basically IDEs for stating and proving theorems. And they can require quite a lot of manual effort to find and write a proof, but checking the proofs is automatic. There are a few widely used proof assistants today, at least in the academic research realm. One of them is called Isabelle Hall. One of its most well-known applications is in a project called L4.verified, or you might know it as SEL4. That's a microkernel operating system that has a full proof of functional correctness. There's another one called COC, which has one known example application, the CompCert formally verified C compiler. And my own work is focused on the COC tooling. And that's indeed what we use in the project that I'll tell you about for most of the rest of this presentation. So with a tool like COC, why should we trust that this process is somehow giving us the idea of truth about system correctness that we really care about? Well, the way it goes is that there's the human user interacting with what we call a tactic engine, which is basically an automated assistant in finding proofs. At every step of this interaction, the human shares what's called a tactic, or a description of a proof step. Tactic engine decides if that tactic applies in the current state of the proof. And if so, it can respond saying, okay, that worked, and now here's what's left for you to prove. And this process continues indefinitely. An important part of this kind of architecture is that the tactic engine can be extended with new tactic libraries dealing with different mathematical theories, or maybe adding reasoning about the C programming language or other examples like that. But all of these libraries need to explain their sequences of logical deductions from first principles using a common language of proof terms. So no matter what complex interaction goes on between the human and the tactic engine, we get a proof term in a common format out in the end, which appeals to a relatively small set of axioms and inference rules. And in fact, this is set up so that everything I just talked through is what we'd call untrusted, meaning that mistakes in any of these pieces shouldn't allow us to accept an untrue theorem, because there's a relatively small proof checker that takes in a term in this format and can algorithmically give us the thumbs up or the thumbs down for it, just following a formal definition of the deduction system. And this system is expressive enough to cover basically all of math and computer science and other domains too, I'm sure. Okay, so let me make this a little more concrete. I'm going to switch up my screen share to show you a different window on my screen. Hold tight there. Oh, and I see a few chat messages going, fun stuff. But okay, other window coming up. I'm going to be using my favorite text editor, Emacs, which, oh, okay. Here it is. Just a quick example of proving some simple theorems to give you a sense that this is a real programming-like process. It's not some wisps of clouds in the sky of pure theory. So we're just going to look at some simple functional programs and prove some basic properties about them. To start out with, I want to use some examples of lists. So I just have the text of some concrete lists written out here. My cursor is moving around in a source file in the language of the Calc theorem prover. This is a list containing the numbers 5, 13, and 89, unsurprisingly. We could also build a list of different Boolean values. And it'll be important that the syntax for list literals is actually desugared into repeated use of this infix operator, double colon, which in the world of Lisp would be pronounced cons. It's just an operator that builds a new list from an old one by adding a new element to the front of it. And this open close square bracket stuff is an empty list. So I'm just running through this as I go and getting some feedback in this pane of my editor, for instance, telling me the type of the expression that I just checked. And here is a simple recursive function defined over lists of any type, which analyzes the structure of a list. And if it's empty, says the length is 0. If it's built with this cons operator, it says the length is 1 plus the length of the tail of the list, the part that we get after we chop off the initial elements. So Calc processes that definition, tells me that's now recursively defined, and I can run some test cases on it, like one of the lists I gave before, whose length is correctly computed. Here's another one of the standard functional programming examples. It takes two lists and pushes them together into a longer list. I won't dwell on the details of how that's defined, but for instance, if I combine these two lists here, you can see down here, they've been combined properly into 1, 2, 3, 4, 5. So if I were just doing regular programming, maybe I'd stop here. I'd of course define a lot more code, run a lot more test cases, but I'd never really be sure my program was correct unless it only had a finite set of possible inputs. So what's even better is to prove the program is correct. So let's just tackle this theorem here, which for all quantifies over all possible pairs of lists and wants us to show that if I append two lists together and take the length, then I get the same number as if I took their lengths individually and added those together. All right, so I'm going to delete this word admitted, which is a placeholder when you haven't done a proof yet. And now I'm in the best part of all this, the interactive proof mode, that at every point is going to show me what I still need to prove and help me figure out what next step I should take in my proof. So I just basically have my theorem statement repeated back to me here. And I'm going to repeatedly make a choice of the next step in my proof. For this one, and like in so many proofs, I want to say this is a proof by induction. Let's do induction on the structure of the ls1 variable. And that's going to give me two cases in my proof, a base case and an inductive case. Each of these is a copy of the theorem statement where the variable ls1 has been replaced. In the base case, it was replaced by an empty list. And in the inductive case, it was replaced by this kind of most general schematic non-empty list where there's some first element A and some remaining list ls1. So I'll just throw in a curly brace here to focus in on the first of those sub-goals. Now I take a look at this and say, oh, well, this conclusion here, in general, we have a double dashed line here. Below it is what to prove. Above it is the variables we're allowed to reference in the statement of what we want to prove. So I want to get rid of this for all quantifier at the beginning of my conclusion formula and I'm going to move this variable above the line, turn it into just another local variable. I can use a tactic called intro for introduction to do that. And notice as I go, the proof state is evolving. Then I take a look at this and say, append is defined so that when its first argument is empty, it just returns the second argument. So let's use a tactic called simple for algebraic simplification, applying the definitions of recursive functions. And now, this looks like a pretty straightforward property to demonstrate. The two sides of my equality are syntactically equal, so I can run reflexivity to prove this case. Okay, so we're halfway there. Base case discharge. This is the inductive step. Now notice there's an explicit inductive hypothesis up here, which looks a lot like a restatement of our theorem, but it's now specialized to a single list ls1 that we're working with. So I can try the same intro step again. I can do my algebraic simplification. I'm not quite done here because the two sides of this equality are not syntactically equal. But I notice, hey, this term here, length of append, is also present in my induction hypothesis. So why not ask to rewrite with the induction hypothesis, finding all occurrences of the highlighted term and replacing them with this other term instead? Let's try that. I gave the name of the hypothesis that I used for the rewrite, and now I'm at the point where reflexivity applies. So I can wrap up this proof. QED is the final step where we generate a proof term in the core language of deductions and check that from first principles as well. So we don't have to trust any of the tactic engine that helped us get here. Cool, so that's our append proof. And just to show you one more example, then I'm going to go back and show how we can do these in a little bit more of a clever way that is more scalable to large software systems. This is a list reverse function, which uses append that I just defined. And basically the key recursive case here is when you have a list that's not empty, you can reverse it by first reversing the tail of the list and then appending to the end a singleton list with the one element that was originally in the front. So for instance, if I reverse 1, 2, 3, I get 3, 2, 1. So I'd like to prove that when I take the length of a reversal, it's actually the same as the original length. One of the best tricks and kind of an intermediate point on the path to enlightenment using these tools is to be optimistic and copy and paste a lot. Things that worked in other examples might work on your new examples. So let's try that here. Well, the name of the variable has changed. That's fair. I'm doing induction on the list that I have, though I don't need to run intro anymore because there's no additional variable. And I'll skip ahead and take it out of there too. So I make short work of the base case. Let's see how our induction case goes. I can try to rewrite with my induction hypothesis. Ooh, unfortunately, it doesn't work. I don't actually have a direct mention of the length of the reversal here. I have the length of an append of the reversal and something else. So here's where I realize, hey, I just proved the theorem about the relationship between length and append. I can rewrite with a previously proved theorem as well. So let's do that. And now if I do some algebraic simplification, I see this is close to proof. By the way, capital S is the successor function, which is a special way of writing adding 1 to something. So these are two different ways of saying add 1 to the length of the reversed list when I apply this fact, which says that the length of the reversal is the length of the original. And it turns out I can call a tactic called LIA for linear arithmetic that's able to take it from here and prove this for me. All right, so that wasn't so bad for examples on this scale, but if you're trying to say, show that your compiler is correct, then you typically appreciate, let's say, higher level deduction steps than the ones that I kind of suffered through here. So a lot of my research is about effective automation in this setting, where we try to minimize human effort in the proofs without giving up anything about the level of rigor. And the way that works in Calc is we use a Turing complete scripting language that finds proofs for us. The name of that language is LTAC, and I'm going to write a simple LTAC program here that will be able to deal with all our goals here. Repeat is a kind of looping construct. And I'll say, yeah, let's try that simple that was working so well. And I'll even apply it more broadly. I don't have time to explain exactly the details of this. Then I call a tactic called intuition that always makes people laugh when they first hear the name. It actually refers to intuitionistic logic. And it's basically like calling an integrated SAT solver kind of thing. And then I'm also going to have Calc automatically look for rewrites instead of making me pick them. Okay, so put all those steps together, say with the repeat keyword to try them over and over again until they don't work anymore. And now it turns out this first theorem really was easy because that's enough to make it work. I'll comment out these more specific details. And my second example, see how easy that is. We almost proved everything, but there's no free lunch here. Basically, where the system is stuck is realizing that the length append theorem that I manually asked to rewrite with is a good candidate for always trying to use automatically. And there's a hint mechanism that we can use to make that work just by registering good rewrites. And that's enough then to prove this theorem. All right, so again, we have a pretty flexible way of automating mathematical reasoning in a very expressive language of theorems. And nonetheless, we get our conclusions with high levels of assurance because everything is compiled on the inside into a small language of mathematical proofs. So I'll just switch back to my slides here. A few more points I want to make before I'll pause and see if there are any questions about the basics here before I go into our application. You might have wondered, I did have to do some work to write out the theorem statements. And for realistic software systems, those theorem statements will get even longer, significantly longer than I showed you. So sure, this method might let us go from complex error-prone programming to complex error-prone spec writing. Is that really progress? Do we just have a new bottleneck in relying on untrustworthy humans? Well, the approach that I generally try to argue for is to focus our use of formal methods and our spec writing efforts on the lower levels of stacks of components in a complete computer system. Systems infrastructure tends to be relatively doable to specify succinctly. It's hard to write a spec for Microsoft Word, but it's actually relatively easy to write a spec for a compiler relative to the complexity of what's going on inside the compiler. Likewise for operating system kernels and other systems that are heavily optimized. That's really the key to this. This is somewhat of a glib oversimplification, but I would say, what's the gap between a spec and an implementation? It's optimizations. So the more optimization a system has, the more opportunity for having a dramatically simpler spec that makes it worthwhile to do formal verification. Okay, but it still might be pretty hard to get specs for significant systems right. Let's think about the example of a compiler, which to be specified needs to have formal semantics written out for both the source language and the target language. And let's say the target is a machine language. We could easily have bugs in either of those artifacts, but imagine we also have an application written in the source language of the compiler and proved against the same semantics we wrote for that language in terms of some high-level spec. And imagine we also have a processor that we're proving to correctly implement the machine language semantics. And we reason in terms of the semantics of our hardware description language the processor is coded in. A cool thing happens if we consider this stack as a self-contained, fully verified unit, where we've proved some nice property connecting the application spec down to the hardware language semantics. All these internal pieces of the box are no longer trusted in the sense that in the process of proving the entire system correct, we must find any bugs that were left in the intermediate pieces, not just components like compiler or processor, but even bugs in proof artifacts like the semantics. If we got the wrong idea of what a certain construct of the C programming language means, and if that construct is relevant for the correctness of the total system, we will find that mistake in the course of doing this complete proof. So this is a pretty significant change in the way we think about quality assurance of our systems. The way we're used to is we need both system integration tests that cover the complete behavior of a system and unit tests that zero in on particular components, because the combined state space of the full system is so gigantic. It grows exponentially as we keep adding pieces in. There's no way we could generate enough system integration tests that we could really convince ourselves we'd covered all the idiosyncratic behaviors of our individual components. But with the style of end-to-end proof that I'm arguing for here, we really only need our system integration theorem. We don't need to make a list of test cases, and we don't need to consider the behavior of individual components. Because if we manage to prove the full system works in all scenarios, then it must be that the individual components work well enough in those scenarios too. And we can replace the traditional careful code review of all components with careful code review, not only with a focus on kind of the perimeter of the overall system, but we can look carefully only at the specification, not the implementation anymore. So that's a dramatic simplification. And it is still true, we have to invest in the proofs of our systems. Even if we don't have to read those proofs anymore to believe the verification result, someone has to write them. and they are huge and unwieldy. But so is a machine code program, and we're used to using all kinds of tooling to automate the process of getting machine code. Compilers, we rely on lots of libraries, and the same thing's true in this world, where custom provers are written, libraries of lemmas are written and reused, and so we can apply all our good ideas from software engineering in this world. All right, so I am going to start now talking about how we apply these ideas in the world of cryptography, but let me also try to see. I guess there aren't any questions posed at this point. I'm just checking.
No, there's a couple.
They're not. Oops, not in the question mechanism, huh? They're in the chat.
That's right. Yeah. Okay. Sorry. Yeah. So we're using the chat. Right. So there was a small discussion about how the holy grail of formal reasoning is actually automatic theorem proving. I think you've addressed to some extent by showing the tactics. We can talk about that. But let me first get to specific questions. So Karim is actually okay. I'm not sure if it's a question or a comment, but here's what he says. I have to disagree on the purpose of unit tests. It isn't just that the system tests don't provide coverage, but that it's hard to understand where a problem lies if a system test fails. So would you like to comment on that?
Yeah, I guess it's a property of this kind of proving that you have to work so hard to prove theorems, and you're just so up close and personal with all the parts of the system you're proving that when you fail to prove your total system, you'll be staring at a particular line in your proof effort. It'll be clear which component you're focused on, which lemma you're proving. And so it's kind of relatively easy to do attribution of whose fault it is that a proof effort didn't go through.
Great. Okay, Roland is wondering, and I get this question frequently too. So isn't specification often larger than the code itself?
Yeah, so this is kind of one of the frequently asked questions I tried to address with my admittedly somewhat cartoonish equation of spec plus optimizations equals implementation. It does tend to be true, though, that the more a complex system is complex because of optimizations, performance motivated algorithm and data structure tricks, the smaller the spec is compared to the implementation. And a compiler is a great example, because you can imagine, say, look at LLVM full of optimization passes doing many clever things. The specification doesn't need to say anything about optimizations. And this is the big advantage for making the spec short with respect to the full implementation. And I think in the case of LLVM, that's probably an orders of magnitude advantage. And similar cases abound in infrastructure software.
Right. All right. So here's slightly more basic questions from EG. Okay, I guess this is more about proof reuse. Will the end-to-end proofs have to be rewritten for different hardware architectures?
So you can definitely develop proofs modularly, where the parts of your system stack that are obviously architecture independent can be proved once, and those theorems can be reused for different stacks that use those components. For instance, just looking at a single compiler proof, you might have front-end phases that are architecture independent and are proved once, and then back-end phases, which, yes, are dependent on hardware architectures, and you do have to prove each new back-end separately. But then you can compose that proof with the proofs of earlier phases and really achieve a lot of effort reduction versus the hypothetical of redoing everything from scratch for each hardware architecture.
Very well. Okay, so here's a good one from Benjamin. Is it possible to prove theorems about algorithms that use randomness and rely on probabilistic reasoning?
I don't know, but I hear there's this genius named Ilya who has it all figured out.
Well, okay, I'm working with the best. So yeah, so Kieran, who is also here, Benjamin, talk to us. We actually have done some work in this space.
Well, I guess a meta answer is really any mathematical argument can be fit in this kind of tool. It's just a question of how much work it's going to take to get it encoded.
Very well. Okay, so there is a question from Roland, and I think it's lacking a little bit of the context. So he's asked, yeah, okay, so right, so here's more from Roland. So the issue with specification is that perhaps the mechanized specification, in the same way, the handproof is very much more compact mechanized proof. I'm not sure how it's an issue, but Okay, Adam, what's
Yeah,
your
I'm
take
not
on
sure I
that?
understand yet either. Let me see if I can
Okay,
talk through
so
this more.
I think we can have a few minutes. So where's Roland? Okay, Roland, you're a panelist now, so you can speak up. Yeah, Roland, you can
Hi,
ask a
hi,
question.
Adam.
Yeah.
Hi.
Perhaps the issue is really perhaps mechanization versus hand stuff, right? So when you write a proof by hand, it is not like in Coq. Like I mean, if you submitted a paper where you put in all the mechanized proofs for your results, the paper would be rejected simply because the paper would exceed the page length. Right, and actually, no reviewer would read it. They was okay. You can say, oh, just run it on Coq or something like this. But I know that they wouldn't accept it, right? Similarly, right, you look at the four-color theorem. Some mathematicians, do not consider the four-color proof as a proof. Right. So, and of course, there's no, it's not that we have the magic bullet, right? Like, but perhaps that is the issue, right? Like, and and perhaps sometimes that's also why, of course, hand proofs are subtly wrong because they miss out some little tiny detail. But of course, often they can be corrected, and they are usually, I think, often is the case that they're not actually wrong. The proof just needs some complicated correction, and so on. But I think that this same thing, will happen. What sort of happens when you push it into the spec. Like I'm not so convinced by the cartoon thing. I think it depends on how you write your software. And of course, I think if you write your software to be more functional, that's probably easier for the spec. But if you write your software to be, let's say, efficient, sorry, let me put efficient in quotes, okay? If you write your software to be efficient, and then it might require a lot of global state, and then the spec might also be complicated.
Well, so it is true that when you're trying to write a specification for a program in a language like C that introduces some complexities, just talking about calling conventions and other details like that of imperative programs that you wouldn't have if you're reasoning about functional programs. But it's not true that the spec needs to say, talk about details of how you represent the data structure in memory. The spec depends on the model of, say, what it is for a C program to execute and how you know what the answer is. That's a generic model about the C programming language, not about your program, not about the clever data structure or algorithm that you selected for it. So I'd say there's kind of like an amortized one-time cost to
but
write the
there's also
spec.
some other complexity we see that if you use the semantics of C, then it's like which semantics of C. But anyway, let's not go there because it becomes that would be boring to the rest of the audience.
Well,
okay.
we can postpone it till the end. Okay, so here's one question actually that comes from Q&A. That's from Abik. How much compositionality are you enforcing in the proof construction, specifically in Coq, so as to ensure maintainability of the proofs? Okay, another question about proof reuse. Any comments on integration with continuous integration, continuous development? Even though I understand that you are recommending proving of system software rather than application software.
Okay. Yeah, that seems like two pretty distinct questions. Let me take the first one first. It is a common complaint of people who are at intermediate points in their enlightenment curve of using tools like Coq that it is hard to refactor, or what's the right word? As you make changes in one part of your system, it's hard to get all the other pieces to be updated to follow your new definitions. And that's a big part of my research focus, is developing automation techniques. So, and this is related to the demo that I showed, transitioning from proofs more like the second style I showed than the first style, where it's less writing out all the steps of the proof, more writing a program that finds the proof automatically. And when you apply that style properly, then you can really get some nice decoupling between the different parts of a system, where you can say you can even change the implementation of a function, keep its spec the same, and find that your old proofs just keep working if you anticipated enough of the kinds of changes that people would be writing eventually, which is challenging, just like it's hard to design an API for software. But as a community, we're learning more about that, and that's a really important kind of knowledge for us to be building to lower the costs of this kind of formal assurance. And then let me take the second question, which is about continuous integration. It's just a great match for this kind of tooling. I think almost everyone doing projects using Calc and related tools is using CI. Most of us are probably even doing it through GitHub and Travis. You've just run command line tools to recheck proofs, and that integrates perfectly well with any CI system. So there aren't even really any big conceptual challenges there. Your code is in version control of the standard kind, and you have a command line tool. You're in great shape.
Thank you. Okay, another question from Karim, which I think was very to the point. So, so the question goes as follows. So perhaps I'm missing something, but how do you go from a description of your algorithm? Karim says on Lisp, but I presume that meant in the language of Calc. How do you go from description of your algorithm to an implementation? Is there code generation? How do you verify that your implementation is actually correct?
Yeah, so there are a tool that, like the one I'm using here, is so general that there are multiple possible answers to that question. But let's just talk about the two kind of canonical directions. Two ways to go back and forth between the real world and whatever's encoded inside the proof assistant. The direction where you go from functional programs, which is probably what you meant by Lisp, though like Ilya said, it's not literally the Lisp language. Direction where you go from functional programs inside Calc into functional programs in other languages like OCaml or Haskell is called extraction. And this is probably the most popular way of taking an algorithm verified in Calc and getting it out into a real code base. And the other direction we could call maybe program ingestion. I don't know if there's a standard name for it. You can write a parser for any programming language, which translates it into abstract syntax trees in a data type defined within Calc. And then you can write a formal semantics for those abstract syntax trees and reason about the results. And there are a number of tools that do this for the C programming language, for instance. As much of a morass as it sounds like to define exactly what all of the constructs mean in a good subset of C, a number of teams have tackled that problem by now. And they have some good tools that you could pick up if you're interested in verifying a C program.
Well, okay, so the last question, probably the rest we can take after the second part, but here it comes. Yep. Okay, so Karim acknowledges the answer. So thanks, Karim. So David is asking, hi, does theorem proving work in proven parallel or distributed algorithms? Oh, good question. While I have heard about efforts to prove the entire CLRS book, I have not heard much about this direction. Well, okay, for other answers, David, talk to us again. We're actually doing that, but Adam does that too. Yeah.
This audience is full of ringers trying to drum up Ilya's research. Yeah, so again, any kind of mathematical reasoning and any kind of any argument that should convince a person can be encoded in a tool like Calc. I'd call it maximally expressive. This is a really hard problem in general, a lot of active research, hard to do justice to it with a single answer. But go to a conference in programming languages and like half the talks will be about it.
Well, okay, I think we can carry on to the second part. And if there are any questions, folks, please post them on chat and we will answer them at the end.
Okay, on to the second part. I'm going to first say a bit more about the kind of code that we're interested in generating in an approved way. So remember again, we're in the setting of cryptography where the gold standard of correctness is properties like this one. You can only generate a signature quickly enough if you know a secret key. And then through a process called protocol verification, we can show that particular algorithms actually meet that requirement subject to standard assumptions. And then through a further process that I'll call implementation synthesis, we can come up with a fast implementation of the algorithm and a proof that it really computes the same answer. project I'm focusing on today is just in that second category, though there's a lot of great work in the first category and in connecting these two kinds of arguments together. So in more detail, we're working in a kind of cryptography called elliptic curve cryptography, where you're dealing with two-dimensional points where the coordinates are integers in a prime field. And the first step of an argument taking us towards an optimized implementation is to show equivalence of an implementation that counterintuitively uses four-dimensional points, because this makes the code faster, since we find ways to avoid needing to run division or modulus instructions, which are relatively slow on commodity processors. And you can use calc, and we did, to prove that the less obvious version really gives the same answers in the end. And these are both functional programs we're talking about for these two layers. And then the next level is to think about how we represent the individual modular integers within these points, the different coordinates. Each integer needs to be split into a bunch of integers that are small enough to fit in the registers of the kinds of machines we're targeting. And so we need our variations on classic arithmetic operations that work on these lists of integers to represent single big integers. And so this is another problem in formally verifying functional programs. And then finally, we apply compiler style techniques to get those functional programs translated into code in C or other low-level languages, with proof that the final low-level version actually computes the same answer as the high-level version. So each of these little curved arrows is a separate formal verification effort within calc, but that can all be composed together to get a theorem that bridges the gap from the top to the bottom of this picture. What comes out in the end? C code like this. This is the same algorithm compiled for two different kinds of hardware, 64-bit and 32-bit. I'm intentionally using a small enough font that you probably won't be too tempted to try to digest everything. The main point here is just that these are not obviously the same algorithm. There are even some operators that appear on one side but not the other. And there are a lot of details that you could get wrong if you tried to write this by hand, even though the experts were doing that before the tools like ours popped out. And we do this in a way that actually guarantees the correctness of this code. So what exactly are the tricks going on here that have motivated writing this kind of code by hand? Well, one of the interesting things about this domain that really surprised me is it really matters which prime modulus you choose for big integer arithmetic if you want to get fast code on commodity processors. Let me give you an example of a really cleverly chosen modulus. 2 to the 255 minus 19 is widely used in secure web browsing and elsewhere for elliptic curve cryptography. It's an example of a category of primes called pseudo-Mersenne, which are large powers of 2 minus small constants. Why does that pay off? Well, let's think about an example of an operation that will run a lot, modular reduction. Let's say I just ran multiplication on two big integers, which naively needs to be represented with twice as many bits as I needed for either of the original integers. And I want to shrink that back down to the declared number of bits for an integer mod, this 2 to the k minus c. So let's say the outputs of the multiplication are split into the higher order bits y and the lower order bits x. And we shift the higher order bits by k positions and then add together to reassemble the big result. I want to compute that mod operation. How do I do it? Well, let's do a little algebra. I'll subtract and add the small constant c in the right places. I'll distribute. And here I've hit pay dirt. I notice my modulus appears as a subterm in the formula. Of course, that's congruent to 0, so I can cross out this term. And almost by magic, I have a recipe for running a mod operation by just executing a multiply by constant, and it's a small constant, by the way, and an addition instruction. And these are much faster than mod opcodes on commodity processors, so this is a huge win. Then let's look in a little more detail on how that multiply is going to be carried out. The result of multiplying two numbers in this prime field would naturally require 510 bits to represent. So let's break that out into 8 different digits of 64 bits each. And we can write the formula on the last line shown here to reassemble those digits into the single large integer. The higher order half of that can be seen as being shifted by 256 bits to represent its contribution. Unfortunately, that is not a 2 to the 255. So we're kind of off by 1, and we can't use that nice trick from the previous slide, and we're kind of stuck running expensive instructions. So instead, on a 64-bit machine, what real libraries will do is break those 510 bits into 10 digits of 51 bits each, so that now the formula for reassembling the big number has a 2 to the 255 in the right place, and we can use the nice optimization. This is weird. We chose a representation that doesn't even use all the bits in our 64-bit registers, but it pays off because of these higher level algebraic properties. Now imagine what you want to do on a 32-bit target. We break each of those 51-bit digits into 2 digits of 25.5 bits each, which can then be reassembled into the big integer with the formula shown here. Now, of course, I don't know about you, but I don't have a machine that has fractional bits available. So actually, we're effectively repeating, alternating between floor and ceiling operations to compute the number of bits going into each of our digits. This is even weirder than the last one, despite being the standard trick used on 32-bit processors, because now we don't even use the same number of bits for each of the digits in our representation. But I hope I've explained here why there are at least 3 different, fairly well justified data structures to represent the single conceptual idea of a big integer that we're going to do modular arithmetic on. So what does this suggest? It suggests we should write a compiler that takes in a choice of data structure and automatically writes the code for us, right? So let me show you a quick demo of what it's like to call our tool. I'll just jump back into my IDE here and go to my shell. Here's a command line I generated in advance. I'm calling one of the variants of our compiler, or our tool, called unsaturated Salinas, which is basically the name of a family of algorithms for finite field arithmetic, as we're dealing with here. This first command line argument is just a name for the code. This is the number of bits in the target architecture. This is how many digits to break a big number into. Digits need to fit in registers. And here's the actual prime. It's important that I've written it this way. I haven't just written it as a normal integer literal. I've given a formula for how I think about the way this prime is computed. And we actually analyzed the form of that formula to make a heuristic guess at the right data structure to choose based on that and other parameters. And then the remainder of these arguments are just names of arithmetic routines from our library that should be specialized to these parameters. And then, without further ado, run this. A bunch of somewhat intimidating C code pops out. This is all proved correct against whiteboard level mathematical definitions. We get some nice comments in the code, including post conditions expressed in terms of functional programming, and also bounds assertions or bounds requirements, depending on whether they're about inputs or outputs. Sometimes the code only works when the input numbers are within certain ranges, or it promises to produce only outputs within certain ranges. These comments are actually checked by the Calc theorem prover, so they're a lot more reliable than your typical comment in a program. And then let's show another example. I'll run a different script, which is calling our compiler in a different way to generate a different common elliptic curve. This is actually, I'm not sure whether this is the first or second most popular curve on the web at the moment. This and the one I just showed together are the first and second most popular. Bit of a more complicated prime formula here. We're targeting a 32-bit platform instead of a 64-bit here. And as this is running, it is crunching its way through our library of algorithms, specializing them to this particular prime. And in a few seconds, we'll get something out here in C code. This one takes longer because, well, it's a more complicated prime, basically. And fewer bits available in registers means we have to work harder, break things into more parts. Here we can see examples of calling compiler intrinsics that we define some alternative names for. Bunch of bitwise operators going on here, fairly intricate stuff, and I'm glad I didn't have to write this, let alone prove it. Got some pages of code here, and more complicated input bounds and output bounds, preconditions and postconditions, and it's all formally proved. And you can run this command line tool and generate new code without knowing anything about how to drive calc. And indeed, we have several users in industry who do just that. So that's the basic idea here. This is the final user experience of applying our compiler. Oh, I do see a raised hand has appeared. This is probably a fine time to take a question. And am I authorized to see the question? I don't know how to act on a raised hand. Ilya, what should we do?
Yeah, so there's one question in the Q&A, but I think it's about the previous discussion about the CI. There's nothing.
Okay, so we can come back to that
specific about the crypto. I think we can postpone that. Yeah.
But then I said Kieran raised a hand.
Oh yeah, here's Kieran. Yeah. So are the comments actually used by the users of the tool?
Yeah, we haven't run a user study or tried to be systematic about seeing to what extent people appreciate these and use them to derive value. So not sure I have an answer to that, but it sure makes us happy to see them there.
Roland, very good question. So what about the optimality of the generated code? I guess.
Yeah, I'll come back to that when I talk about the evaluation part of our project.
Okay, no more questions so far.
Okay, so I'll go back to slides. Okay, so how does the magic happen under the hood? So as I've just shown you, the way this appears to the user is the library takes in a choice of a base system representation and outputs fast C code. What's not to like? And the library itself is actually proved as a kind of domain-specific compiler to always output correct C code. How does it accomplish this generation process? We've invested in creating a library of functional programs for standard arithmetic operations. And these operations are parameterized on the prime modulus and the base system data structure selection. And these operators are proved once and for all in roughly the style that I demoed earlier on. Then when particular parameters are confirmed, we apply a classic compiler technique called partial evaluation to specialize the code to those parameters. And the result is flatter functional programs that look more like C code. And they're flat enough that we can apply additional compiler ideas to turn them into literal C code in a proved correct way. So let me go through those different steps in more detail. Let's again stick with the example of multiplication. I'll pick a simpler modulus 2 to the 127 minus 1, where we might on a 64-bit platform represent a single number with 3 digits reassembled into big numbers with the formulas shown here. When I multiply these together, we get out, well, 9 different cross terms, which I've arranged here suggestively in a number of columns. And the idea is we're going to compute a 5-digit representation of the output of this multiplication, which is 2 digits too many with respect to what we want eventually, but we'll get there. So I'm just going to add down the columns. Each column has very close together, if not exactly equal, powers of 2, which makes it straightforward to write out the formulas for what digit value appears in each column. And then we could reassemble those digits into the overall big number with this formula down here, where we notice I've factored out the 2 highest order digits to be multiplied by 2 to the 127, which is congruent to 1 in this modulus. So we can kind of cross out that term and move them some digits around, and we get now this nice formula for a 3-digit result of a multiplication using only pretty elementary operations on the digits that came in. So this is what we're aiming for in the code generation process. And maybe you can believe that you could write out a general multiplication routine that's parameterized on the digit representation. And you could even prove it maybe on paper at least. And we did that. We proved it in calc for not just multiplication, but a library of the other kinds of routines that you need for cryptographic applications. So then you have your proved multiply. It's effectively a program parameterized by the digit bit widths, which I'll think of as a compile time parameter, and the digits themselves, which we can call a runtime parameter, and it outputs the digits of the multiply result. So we then specialize that to the compile time parameters, and then algebraically simplify it to take advantage of new information to get a nice lean multiply that handles just the scenario that we care about. Here's where I'm going to geek out a bit for the people who know about functional programming or formal methods and mention that the first specialized step can really be handled as just partially applying a curried function. Don't worry if those terms are unfamiliar. Second step is actually a really central built-in operation in calc and any other theorem proving platform in this tradition. We do a lot of algebraic simplification in pretty much any proof, so there's some great support for this already in calc. That doesn't mean we didn't have to solve some really interesting PhD thesis-sized performance challenges here, but I'll save those for another time. So once we have those routines that have been specialized, well, let me show you how we specialize them first. The first line of this example with quoted code here defines a function w that takes in a digit position I and returns the coefficient for that digit expressed as a power of 2. And then we can write a goal like this example code block, which basically says take in 10 tuples of integers, capital Z for integers. Those tuples are f and g, and compute the output fg, which is another 10 tuple that is the correct result of modular multiplication using a function called eval that turns 10 tuples into big integers according to the representation w. So we wrote some tactics that can automatically generate this output, this 10 tuple that expresses how to compute those output digits as a function of the input digit values, and we get out also a proof that this is the, or let's say a correct formula for this multiply result. So we're almost there to C code. Let's say for sake of explanation, we had a formula like this one instead, and I want to get C code out. First thing we do is we turn it into an explicit syntax tree, the way you would in any kind of compiler. And then we apply standard compiler optimizations like constant folding, which can do some algebra at compile time and shrink that expression down to something more like this. Then we can flatten it to introduce names for all of the intermediate expressions. And here's where we deviate the most from a standard compiler. We want to infer bounds for all of the variables. So X and Y are effectively the inputs of this program. Let's say we knew those bounds for them. Then we can push that information through all of our intermediate operations. We learn that C has these bounds, D has these bounds, and therefore we notice, hey, both C and D are larger than 2 to the 32, but smaller than 2 to the 64. That means I probably want to put each of those in a 64-bit integer type in my C code. So we assign each intermediary to the smallest C integer type that can fit it, which is important for performance in general. We actually started effectively with infinite precision integers, so it was important to get these finite precision types to get idiomatic C code to pop out in the end. So all these little downward arrows are associated with proofs in calc. They all compose together. The result composes with all the other steps that I told you about. All right, so now we have this tool. A little bit about the way the implementation works. I showed you those command line scripts, which use heuristics to analyze the way a prime is written out as adding and subtracting a bunch of powers of 2 to guess at the right data structure. And nice thing about that kind of heuristic, it doesn't need to be trusted at all. Any choice will generate correct code. It's just that bad choices might give you slow code. So we can even try multiple choices and benchmark them to automatically pick the right option. Okay, but what benchmark should be used to make sure this works well enough in practice? Where do we get a lot of prime numbers that are good choices for this kind of arithmetic? What we did was we looked at a popular online mailing list about elliptic curves, and we automatically scraped it to find all the prime numbers written in this way. We got about 80 different primes in that fashion. Only a few of them turned out to be postings by newbies who don't actually know how to pick primes properly, and no one knows how to implement those. So our compiler might time out for some of those. But on all the others, we ran things through the compiler. And here's a graph showing performance on a whole bunch of different primes. X-axis is how big the prime is. Y-axis is how much time it takes to run the benchmark, which I think is a few different Montgomery ladder steps for those who know the lingo of this domain. We're comparing here our generated code with the GNU multi-precision library, which is the previous highest performance, completely generic way to implement big integer modular arithmetic. And there are two different variants of it, which have different security properties, but comparing to either of those variants, we see our code is usually quite a bit faster, typically in the range of 5 to 10 times the speed. This is targeting a 64-bit laptop with an x86 processor. We also ran similar experiments targeting a 32-bit mobile phone with an ARM processor and got pretty similar results, often 5 to 10x range kind of speed ups over what GMP could do. Now, of course, the experts out there were handwriting this code in popular crypto libraries, not using GMP. So we should compare against those as well, even though quite a bit more work goes into building one of those specialized implementations. So let's look at our code versus OpenSSL. We are faster than the cross-platform C code of OpenSSL, which, to be fair, almost no one uses. They use the assembly instead. But in general, our compiler was able to produce the fastest known C code for all the elliptic curves. And then if we look at the handwritten assembly, which can use a few other tricks that our compiler doesn't know about, we're about half the speed of that code. And we are interested in closing that gap. But at least we're caught up with the state of the art for C code. All right, so yeah, the last part that I'm going to go through here is just talking about a further direction to broaden the scope of what we're able to generate and reason about. But this is probably a good point to take a round of questions, if any have accumulated or if people have had them cached just in their brains. Let me bring up this question thing again. Where do I find that? Whoops, and it keeps doing not what I wanted to do.
Okay, so Roland is wondering, okay, I guess this has been answered. So the GMP is not specialized, so the comparison is probably not fair. Is it so?
I think I kind of answered that in the course of the slides where I got to a next comparison with the handwritten code. We also compared with Curve 25519 implementation, and there we actually did almost match the performance of the best assembly code. But I picked a hard example to highlight on the slides.
Well, yeah, and the second question from Roland. So Roland, how about I just unmute you so you elaborate what you're asking?
So I understand the purpose of the project is more about verification, but for this particular problem of having the fast crypto code, wouldn't some kind of program synthesis be appropriate? I don't know if there is work done in that direction or not.
No, I'd be completely okay with characterizing the overall problem here as a program synthesis problem. Although generally, when you can build a compiler that predictably outputs the kind of code you're looking for, that can be a pretty good strategy. And that is what we did here. We built a compiler and we proved it formally. And now we can rerun that for every different algorithm variant that we're interested in without having to do new proofs.
Right. But I think the program synthesis people sort of do things in a slightly different way, right?
Okay, so I guess you're just asking about a different subcommunity of formal methods and whether anyone has tackled this particular problem there. And I'm not sure. I'm not remembering any particular projects. There's definitely other work in verification of this kind of code where it's been written by hand.
Or you could use super optimization or something like this, right?
In theory, that should be doable. I just don't know any work that has managed to carry that out.
Presumably the super optimization one will be proved to be optimal, whereas this one may not be proven to be optimal.
Oh yeah, we don't prove it to be optimal, that's for sure.
Right.
That would be pretty challenging, I think, to do that. I don't know an approach that even on paper anyone knows how to prove optimality for this kind of code, but it's a great direction for future work.
All right,
thanks.
Thanks, Roland. So a question from Abik. What about hardware implementations? Have you benchmarked against them?
Wait, I'm trying to understand that. You mean varying the kind of hardware? No, I think that maybe it's a question about proving hardware implementations, maybe implementations of the same routines, but in hardware instead of software. Okay.
Right. Yes. So the latter. Yeah.
Yeah. So I guess the short answer there is no, though we've thought about it. And I will be talking about hardware proofs in the next segment here, but that also would be a great future work direction.
Good. Okay, so a couple of questions from Karim. So how much does the user need to know about about all this? So do they need to have the knowledge of which primes to pick, or is it done for them?
Yeah, the user does need to pick a prime to call the tool from the command line. Typically, these are, for many scenarios, someone is writing code to implement a standardized protocol, and then the prime is specified in the protocol spec. But we don't in general provide any help picking which elliptic curve you want to work with. And that's definitely above my pay grade. I couldn't suggest them to people either.
Might be dangerous going by previous cases of picking anything you like.
For sure, there could be all sorts of thorny security issues if you just pick one out of the air.
All right. Okay, so another question from Karim. Is it intended to replace elliptic curve libraries like Sodium, or to be used inside of libraries such as SSL or GPG?
Maybe I don't understand the distinction here. What's interestingly different between Sodium and, say, OpenSSL? But hey, we want to take over the world. We want everyone to use our code. It's intended to work for all those scenarios, I think.
Right. Okay, Karen was wondering, can you compare the choice of prime for performance?
Oh yeah, it makes a huge difference what prime you pick. Most of them are going to be so far behind the ones that are actually used in popular internet standards. But I don't have any numbers ready to quantify that at this point. Maybe that's about the most I can say.
Okay, so I think we can have the rest of the questions after the end of the talk.
All right, yeah. So let me just tell you a little bit more about some current work to expand the scope. Not directly related to those last questions, I suppose, but some commonalities. Here's an example of a system we built on the path towards a fully verified cryptographic application. There's no crypto in here yet. This is just the foundation for it. This is the verified Internet of Things light bulb. Here's an Ethernet card. Here's a power strip with a light bulb connected to it. And here's an FPGA connected to those two, running our formally verified processor and software stack. So when the right packet arrives over the Ethernet card, surprise, the light bulb turns on. And our theorem basically covers everything digital that's loaded onto the FPGA, hardware and software, with a unified theorem of functional correctness. So the right kind of specification for this sort of system, as we think about the hardware and software as a black box together with some IO pins carrying bits, and we consider all traces the system could generate, where on every clock cycle we measure the pins and see where the ones and zeros are. The input pins are under the control of the environment. We need to be ready for any values they take on, but the output pins are ours to specify, saying exactly which outputs are legit at each moment based on which inputs came in up to that point. So we can write a spec for this system saying the output pin controlling the light bulb is on exactly when the last valid Ethernet packet said it should be. So our proof is organized in layers with some nice modular structure. At the center of it all is the hardware instruction set. We use RISC-V, an open instruction set that you can actually implement in your own hardware and not be sued. We build and formally verify processors using a hardware library called Kami that we designed. We have our own systems programming language called Bedrock, which has a formally verified compiler, as well as tools for proof of individual source programs. And that allows us to write and verify the controller software, both what we'd call device drivers and application code for this particular system, and prove against that trace predicate I sketched on the previous slide. As I emphasized way back near the beginning of this talk, a cool thing about this kind of architecture is when we view the layers together as a proved black box, we do need to make sure we got the spec right at the top and the bottom of this picture. But everything inside the box is no longer trusted. Bugs there no longer endanger system correctness as long as we manage to finish the proof and if we pick the right spec. So don't worry about compiler bugs, processor bugs. Also don't worry about bugs in your instruction set semantics and so on. If we proved it end to end, those must be good enough. So building on a system like that, how can we reach towards proofs that cover larger fragments of cryptographic systems? And thinking about this stack of layers in cryptography that I had shown before, if we want to connect more to those abstract security properties at the top, we can head into the world of protocol verification, maybe building on work that Andrew Appel and his collaborators have done, showing that you can indeed use calc to integrate protocol verification with functional correctness proofs about C programs and even formally proved compilation. We've been developing a new higher level functional programming notation for protocols that should be helpful for this. We'll be presenting it at the POPL conference in about 2 weeks. Then, as we think about taking this correct by construction generation technique and making it work for larger parts of crypto libraries, not just the big integer arithmetic, we've developed a platform called Rupicola, which is able to do that sort of thing for a broader range of functional programs that actually need features like loops, function calls, and imperative data structures in the generated C code, which you might or might not have been obvious from what I showed. The classic Fiat crypto system doesn't handle any of those features. And to close the performance gap with assembly code, we're collaborating with Professor Yuval Yoram and others at the University of Adelaide to apply genetic search. This might be related to that super optimization question in some sense. Genetic search to find the best assembly code that computes a particular function by mutating known good examples and connecting that to formally verified equivalence checking to show that the assembly program we find really does compute the same mathematical function as the code we started with. And finally, we're looking at connecting the results with formally verified hardware and system software like device drivers along the lines of the preliminary case study I showed you a picture of for our verified Internet of Things light bulb. So the goal here is to build example applications like even a private messaging client, kind of a standalone terminal for speaking a protocol like Signal for talking to your friends without anybody eavesdropping, and having an end-to-end theorem that this hardware design with these initial memory contents of machine code will realize this high-level abstract security property with everything in between proved in a nice unified way. So I'll close the presentation part of all this with these two URLs to find the main projects I talked about on GitHub. We're always glad to take pull requests and answer questions. And indeed, I'm happy to answer any more questions here. I guess we have about 5 minutes left.
Thank you so much, Adam. Really nice talk. And there are more questions, actually. So Roland is wondering, so how the Fiat effort compares to Project Everest from Microsoft?
Yeah, so Project Everest applies what I'd call verification as opposed to the synthesis direction that Roland suggested would be a good term to apply here, basically going from the spec to the implementation rather than having it an implementation and proving it against the spec. Project Everest does the verification element. There are some parts of the bigger picture of a complete protocol implementation that they've already done and we haven't yet. And there's some parts that we've done and they haven't. Like, I don't think they have any significant component of connecting to verified hardware or even compilers that are themselves formally proved. But they've done some of that higher level protocol security reasoning that we haven't gotten to yet. And both of our tools are used in Firefox these days, so there's a little friendly competition afoot.
All right. Okay. So there is a question from anonymous attendee in the Q&A, and it goes. It's again about CI. So the question apparently was not addressed in full, so the person is wondering. So the programming environment can be integrated with theorem proving. So it's how to construct the specification, how to debug the proof, how to maintain the proof are a large issue, arguably for which there is no full solution in the context of continuous integration. And the question is how much support is available for that in the COC infrastructure.
Yeah, I think debugging proofs to me sounds orthogonal to CI, but constructing the spec, it's not obvious how CI would help with that. But there are all these software engineering style activities that you're right are probably different in interesting ways in the world of large proofs. And people who do this kind of research are dealing with that sort of stuff every day. So for instance, we debug proofs by stepping through them interactively and seeing when something goes wrong, where say some library changed and it has an effect on your proof sequence and things don't quite go the way you think. Step through the proof interactively, watch the proof state at each point, fix the issue at the first step where you see something go wrong. And there are other answers like that for other parts, other aspects of this that you've identified. And I probably don't have time to go into the details, but you can see my book, Certified Programming with Dependent Types, for at least the beginning of an answer.
Well, thank you. So Kieran is wondering, in terms of performance, how does Fiat Crypto compare to Everest? So does Fiat suffer because it's more synthesis than verification?
Yeah, this sort of comparison can fluctuate as new versions of compilers like GCC are released. But at least when we first published our paper, we're basically have the same performance as Everest. No interesting difference that wouldn't flip around when you get a new GCC version.
Oh. Yeah, okay. So Abik indicated that he has a question. So please, Abik, go ahead.
Hi, Adam. Thanks
Hi.
for your presentation. Very nice presentation. So
Thank you.
I would like to follow up. I guess my question was quite short, posted in the chat about hardware implementations. The reason I was asking is also related to this point of program synthesis, which was mentioned earlier, because given the way these crypto libraries are written, taking a program synthesis approach where the hardware, arithmetic operators sort of kind of directly relate to specific hardware implementations, or rather hardware units. And then you can synthesize something like, well, in the vanilla case, something like a Verilog implementation. Or if you are looking at the more recent trends, there is a very big trend on the SDH, software defined hardware. So one can even look into those kind of things if one wants to be more topical. So that does appear like, at least appears like a reasonable fit, means that is at least another way, as opposed to the way you have done it. So my, I guess what I was trying to suss out is more like, I'm curious to know why you did not consider that. Maybe there are certain things, because I have not applied my mind to this problem. So maybe there are certain things I'm missing, that this is the right way to go, this compiler approach, as opposed to the synthesis approach where the arithmetic operations kind of directly get sort of converted to hardware. So why you didn't consider that? I think that would be useful to know.
Yeah, so I guess the main reason not to just generate a full hardware implementation of one of these routines is just the cost of fabricating new hardware. We have worked with companies that have built their own crypto accelerators with fixed interfaces, and we're able to tweak our compiler to take advantage of the special instructions that are available on those platforms. But it would also be really fun to say have our compiler toolchain generate a mix of hardware and software implementations that are meant to play well together to implement the functionality. And we are looking at that from a verification perspective so far, but proving programs that mix verified hardware accelerators with software and formally establishing the correct interaction of those pieces. And we might very well find ourselves looking at something more like you're suggesting in the near future.
Thank you. I was just asking because the search space, then it would seem would be quite manageable in such an approach, because you have the arithmetic operations, it's kind of going into a hardware implementation, you have a synthesis approach, and also there is this recent trend, DARPA has this very big program on the software defined hardware, right? Very large investment.
Yeah, but I'm not sure how simple the search space is though, because the naive solution, just building a big combinational circuit, would probably have really bad area properties. So you'd have to do some clever stuff there.
Yes, surely. Thank you so much. Thank you.
Sure.
Well, okay, so more questions, but perhaps we should wrap up. So the last one, which assumes a short answer from Karim. So how far along is verifying security properties of cryptographic protocols? For example, if someone were doing research on distributed cryptography, Greek cryptography, would it be possible to use these tools for proving security?
Yeah, so there's been a lot of work going back decades on crypto protocol verification tools. And I'm not sure when the first research using a tool like Calc or Isabel Hall for this sort of thing was, but I first became aware of it in the 2000s, I think. And so there are a bunch of libraries that you can use inside a proof assistant to do those sorts of proofs. I don't have firsthand experience, but there's some really cool work that I cited briefly by Andrew Appel and his collaborators that not only does those proofs in Calc, but also connects them to correct implementation in the C programming language of the same, not protocols actually, but cryptographic primitives at least, and then uses a formally verified compiler to get this nice kind of end-to-end result.
Very well. Thank you so much. All right,
Okay.
I think it's time for us to wrap up. Thanks a lot again, Adam. It's been a great talk and great to have you.
Glad to be here. Thanks.
Yeah.